Well, welcome everyone. Today we'll be discussing how to make distributed systems fast and cheap, which are two objectives I wouldn't necessarily use for distributed systems in the first place, and how I honestly cheat to, to get there. I tried really hard to squash a lot of information within a 20 minutes talk, so I really hope I'm not talking too fast, and I also want to leave some buffer for questions. Before I start, let me introduce myself very quickly. I'm Michele, and I'm a co-founder of Orama. And for those who don't know, since we are pretty new, let's see if it starts there. No, it doesn't. I wanted to show you a small video of what Orama is. So basically, you can think of Orama as a product answer engine. So you can think of it like Perplexity plus Elasticsearch all together. So you can run full text search, semantic search, so vector and hybrid search all together. You can generate answers, you can chat back and whatever. And essentially, it's a high-performance distributed product answer engine. And it's based on an open source project, which is called Orama. I started building that a couple of years ago as an experiment in one of my former companies. And before I get any further, I want to assure you this is not a sales pitch. I don't want to sell anything to you. I just need to give you proper context of what we'll be discussing, because this is basically a case study for me on how we managed to get there with a lot of improbable choices, I would say. And this is the result. So this is something an image I pulled from our Grafana dashboard on Friday, I think. Yeah, it was the second. So right now we're serving thousands of requests per second with 100% uptime without DevOps. So that's the personal achievement, but also for the company, it's pretty nice because we are like a nine people company. We are a few months old, so it's pretty good to be there at this scale. And when I talk about scale, we are hosting free search for a lot of big open source projects like Node.js.org, JSR, which is a package registry for JavaScript packages, Dino, Remix, stuff by Meta, and more and more and more. And now that we understand the scale, and we will also see the numbers on the performances, because that's also pretty important, right? I would like for you to guess in which language did we implement Orama in the first place. How many for Golang? 1. Rust? JavaScript? It is JavaScript indeed. For a simple reason. So first of all, JavaScript is the king of programming languages. We are all Okay, I see there are some disagreements. I will get there soon. There is a cool reason why we choose JavaScript. Also, I want to be honest. It's JavaScript plus a bit of WebAssembly compiled down from Rust. We tried Zig, we tried C++, eventually Rust. It is a very nice language to write WebAssembly code. And this is where I'd really love to start talking about my functional programming background, because even though Orama is built on top of many imperative concepts, for many reasons, for example, I would really discourage you doing recursion in JavaScript. For example, it's not a memory-safe language in that case. You go Stack Overflow very quickly. But Orama is composed of many little functions that could be considered as pure. So you get an input, you get an output. That's it. Most of the time, you only get one input, just lambda calculus style, and you always get an output, which doesn't reflect on the global state of the application. Even though, I want to be honest, the internal reasoning of the function can have mutations, but it's all self-contained within the same function. The reason why Orama is entirely built up of little functions is because we can replace them very easily in different languages when needed. Like if I need to run Orama on the browser, JavaScript is fine. If I need to run it on the server, maybe a bit of WebAssembly in certain places can be a bit more beneficial. So I'll give you an example of that. This is a function that determines if a tree, an AVL tree, which we use for searching and filtering through numbers, if balanced or not. So as you can see, that's actually open source code you can go and check out. We pass the root, so the entire tree, to the function, and the function has to traverse the entire tree. So we don't rely on a global state. If you think in terms of Java classes, we don't have a class tree, and we access that state So we get the entire tree through the JavaScript function, and it's telling me it's balanced, yes or no. An example of what I mean by substituting certain functions with Rust is this example. So this is still the AVL tree. I don't know how many of you are familiar with that specific tree, but to be very quick, it's a tree that guarantees balance. So all the branches of that tree are perfectly balanced, and they have, and every time I insert something inside the tree, I have to make sure that the tree itself is balanced, and I also have to perform certain rotations for certain nodes in order to ensure, again, balance, and then high performances at search time. So this is an example. So AVL rotate left. This is where I have to rotate left an entire branch of the tree in case it's not balanced. And I take the node, which again is the entire tree actually, or the node itself, and then just perform the rotation and return the new node. As you see, there's a lot of mutability getting in the way. So I'm not saying this is pure function, but the concept of never editing the global state, that's something I brought from my Haskell day, and have been very beneficial. So I wouldn't really recommend using WebAssembly for this particular example. I don't know how many of you have experience in WebAssembly, but if you use WebAssembly on any runtime and you have very little data, the serialization and deserialization cost of calling WebAssembly itself, it's very high. So in that specific case, for example, it's not really needed. That's just an example. I want to disclaim that. So the entire product we are going to discuss now, it's built on top of this concept of very little composable functions with no effect on the global state. And the craziest thing is that we are serving millions of requests right now with one single multi-tenant worker that takes care of full text vector, search, RAG, embedding generation, summary generation, and more for more than 1,000 users at the time of writing. So how is that possible? I'm finally happy to be able to show this architecture, which is the core concept I'd like to show you, and the reasoning on how we got there in the first place. This is likely the most scalable architecture I've ever realized in my life, and I'm super glad to be working on a team that allows me to get there. We will get back to that architecture. I just want you to picture that we will get there, and why is it so different from anything else, hopefully. So the real problem we wanted to solve is scalability. If you have experience with Elasticsearch, for example, keep in mind Orama started as a full-text search engine, then evolved into something a bit different. But if you think of Elasticsearch, for example, when you want to scale, you have to understand what scalability means. So I found this very nice quote from the Lucidchart blog that says, the scalability is the measure of how well the system responds to changes by adding or removing resources to meet demands. An example. Let's say we have an Elasticsearch cluster, and I want to be honest, I love Elasticsearch. You don't get into the search algorithms if you don't love the existing solutions, so I'm only taking that as a golden standard for search. Not because I want to talk bad about it. That's not the reason why I'm talking about it. So if I get more requests, I have to compete. I have those requests competing for the same resources. If I have more data to manage, they are still competing for the same resources. So let me give you an example. I have an e-commerce, and during Black Friday, I have to probably overcommit my resources because I don't know how much I'm going to scale. I know that last year we had to scale a lot. I know the history of how my product scales during unpredictable peaks of traffic, but the reality of the thing is that we always overcommit resources. When it also comes to large indexes, we have to push a lot of data, and eventually you will have to scale horizontally by buying more and more servers, and that's extremely expensive. So in a typical scenario, when we talk about scalability, we get more requests or more data. We have less resources for each request. We need more computing power, so scale vertically, or more servers, so scale horizontally. The cost increases, maintenance and coordination of the data gets messy, and eventually you get to Kubernetes. And I love Kubernetes, but I'd rather not, right? Especially in a 9-people startup. So functional architecture to the rescue. I understood that, like, the first time I said functional architecture, a friend of mine who's a software architect told me, like, functional architecture is not what you're referring to. We discussed the architecture of Orama, and he said, no, that's esoteric. That's not functional at all. So I'm going to call them esoteric from now on, but the reasoning behind the functional name is that takes huge inspiration from the Erlang and Haskell days, and now we are finally get to discuss those. So first of all, the very first thing you have to do when you build a search engine is to identify what is going to be the bottleneck at scale. And the state is the root of all evil, as functional programmers taught me, right? So the real problem when you have to manage databases, eventually it's going to be state. And we have an entire theorem to determine how we want to manage that state. So in a distributed system, you can't simultaneously guarantee consistency, availability, and partition tolerance, so you can only prioritize 2 out of 3. And typical examples we have is like CouchDB and Cassandra, which prioritize availability and partition tolerance. That's eventual consistency, for example. Or MySQL, SQL Server, availability and consistency, and then partition tolerance and consistency, that's Redis, Mongo, and HBase. So all of this is to keep the data on track. So if we scale the server, the database, horizontally, and we have more nodes, we want all the nodes to have eventually the same data. We can do that in multiple ways. We have many models of consistency, like strong consistency, eventual consistency, sequential consistency. We have many models, but they all have to respect that CAP theorem. An example is Elasticsearch. Again, as a golden standard for me, Elasticsearch is AP by default. In fact, it's not uncommon to query replicas that doesn't have data due to eventual consistency. And to be fair, eventual consistency in a typical Elasticsearch cluster takes place in like 60 seconds tops when the system is very busy, so it's very performant. I don't want to say that's bad. Elasticsearch, in fact, it's very good for real-time data. And when we talk about availability plus partition tolerance in that context, just to give you the full picture, is the ability of the system to always respond to requests, even if certain parts of the system are experiencing failures, and the ability to continue operating despite network partitions or communication failures between the components of the network itself. So the real problem when you have to manage data at scale in an architecture is keeping nodes consistent. And you have to reach consensus on what the data is the correct one amongst all the nodes in the cluster, right? Elasticsearch does that with a custom consensus algorithm, but typically you want to use Raft, Paxos, or any evolution from there. And no one ever has told, like, we should write a Raft. Like, you always borrow the libraries from somewhere. And that was a problem for us specifically because working in JavaScript, there's no cool Raft implementation right now. So we had to play a bit smarter in that sense. Then I don't know if in the States you have this image. I'm European, I'm from Italy. We have this image of a little angel and a little devil on the shoulders that talks to me. In that case, they're both Haskell. Very evil, both of them. And I have this little evil Haskell that says, you don't have a problem with state. Stop talking about state. You have a problem with its mutability. Wow, that's a good realization, actually. And its mutability really needed in such a distributed system. So in the context of search engines, again, is mutability something that we really need? We did some market research. How often does a document set change? So we have financial data every second. We have sports every minute. So if I host a sports website and I want to keep scores, or bet, like gambling, whatever, that's data that's changing every second or every minute. Elasticsearch is a perfect match. But if we think of a product catalog for an e-commerce, on average, we discovered that the data changes 3 times a week, at most 2 times a day. Documentation, so product documentation changes like 4 times a week, at most few times per hour. And what about websites, blogs, software as services, and other cases? Most interviewees declared that they'd be okay with an hourly cron job to update the data. So this is the kind of architecture we build. And this is the high-level picture of the architecture. We go to a data source, we gather the data, we create some partitions, we push the partition to a CDN, and then the client just goes to the CDN. You may be wondering, why the hell a CDN? Well, first of all, you can only write JavaScript on a CDN, and that's a good reason for me, so I can keep writing JavaScript because it's fun. Maybe not the best of ideas, but a CDN has different good motivations. First of all, insane scale. So most CDNs, if you think of Fastly or Cloudflare or even CloudFront, they all are able to mitigate like DDoS attacks, for example. They're all able to be closer to the user. In our case, we deploy that index to 300 global locations worldwide. We're going to see a map in a moment. And the CDN, it's now capable of running WebAssembly and JavaScript, so that's a very nice way to distribute the code and the search index itself. In fact, what we do is we consider the index as immutable. We pull, and whenever we need to update, let's say with a cron job every hour, we pull the index delta. We shard the index into multiple indexes, smaller indexes, so subtrees typically. We distribute the updated partition, run health checks, and eventually release a new version. And that takes like 5 minutes on average. We have a new version cooking, which is taking like less than 1 minute on average. And I have still this little Haskell boy that tells me like, I think I told you something about immutable data structures. So the problem with that approach is that every time you have to rebuild the entire index, right? But if you go see how Haskell, for example, deals with immutable data structures, that's golden, that's pure genius to me. And this is where we took inspiration. So in that case, the user can push edits. Orama opens a transaction and keeps ingesting edits. Then Orama commits the edits when it's done and uses structural sharing, just like Haskell for its data structures, to update the individual partitions and push them to a key storage, basically where they're going to be stored. Orama will redeploy all the partitions in a single transaction. The reason why we redeploy those en bloc is that just like with functional programming, you don't edit the global state. We take the global state, we edit, and we deploy a new one. So there's no conflict between the nodes. We can redistribute the load if the nodes gets unbalanced, etc. This is what the network looks like as for today. So it's 310 global location, 120 plus countries, and it's a system which, following the CAP theorem, it's AP, and it is eventually consistent within 60 seconds from when we push the button. So Orama, in that case, it's very good for read-intensive applications. Has a strong caching mechanism, because at this point, you have an index that it's immutable. You know that the data is not going to change. You don't have any complex caching validation rule. So you can have aggressive caching. You can have aggressive pre-caching. So while you're deploying a new index, you have knowledge of all your past searches, and you can start pre-caching the new ones, because eventually it's going to always make the same searches. That's what we found. Nodes are completely isolated. 300 nodes worldwide. If one takes fire, the other one's no big deal. And again, CDN is built for massive scale, so that's good. Now talk numbers. On the left, and I'm sorry I couldn't go back more than this, but from the 7th of February to the 15th of February, we were in beta. And we experienced an average of slightly less than 300,000 requests per month back then. Then we deployed the Node.js website. Then we deployed Dino, etc. And from February the 15th to March the 15th, we started experiencing 608 million requests per month, from one day to another, with peaks at 1,400 requests per second. And the average round-trip time is 100 milliseconds worldwide. So the reason I want to show you this is that, first of all, if you go see on the left the CPU time at the 15th percentile, that's 1.6 milliseconds, when we were receiving less requests. When we are receiving more requests, that's like less than half of the average CPU time. How is that possible? Well, it's warm cache. Like the idea that the index is immutable, the idea of pushing immutability at the edge allows us to, first of all, avoid hitting the worker itself every single time, which is still good. And the second idea is that the more requests I get, the more the warm cache is going to be alive, and the cheaper eventually my request is going to be. Because hitting a cache, it's a lot cheaper than actually pulling data from a key V, performing search, etc. So that's what we did. And this is the architecture that it's actually supporting this. So we have full text search, hybrid search, and summary generation for now, and they all go through the Cortex cache, which is a custom machine learning algorithm we built to determine if that specific query should be cached or not. So if we find it, you can think of it as a Bloom filter to understand if we have it in a cache or not. Eventually, we reach the worker, and the worker is an edge worker on Cloudflare in that sense, which will pull data from shards, which themselves are warm cache. Eventually, if they don't have anything in cache, they'll go to a key V storage that is distributed within the network itself, put back the data, perform search, store in the cache, and we are very likely to serve the second search within like 50 milliseconds, including network latency from now on. So what we learned? We learned that functional programming and software architectures must not be so different. We know that from the Erlang days, maybe Elixir now or Gleam, but now it's clearer than ever that you can apply concepts of functional programming to software architectures, and this pays off. So index partitions, we treat them as immutable data structures. CDN workers as isolated processes, and I'm thinking of Erlang right now, or key V storage as an immutable state. And I don't have any more time, so I'll thank you for being here, and you can find my contacts there. I'll be around if you want to chat. Thank you. If there's any question, I think I have like 3 minutes or so. Sure.
I missed the portion where you said you had no DevOps.
Mm-hmm.
How are you deploying this again?
So it's
maybe you skipped that.
no, it's cool. I haven't talked about that. So it's GitHub workflow, really.
Oh, really?
We push like to develop, like Git flow, like push to develop, goes in staging, push to master, goes to.
What's the bare metal machine?
It's not bare metal machine. It's like we actually push all the code on the CDN directly.
CDN, okay.
Yeah, we have blue-green deployment there, so we have checks, etc. But they all have to succeed within 60 seconds for us. Okay. So if it's not succeeding within 60 seconds, we consider the deployment failed, and we retry. Like there's a lot we can do, of course, but eventually it's all within GitHub in that case.
Sounds good.
Yeah, thank you. Any other question? Good. So see you around.